Hello guys, good afternoon. So this is all about linear systems still, and we are on the iterative techniques. So last time I did a lecture on the Gauss Jacobi and the Gauss Seidel method, which are in principle the same, but on the strategic approach a little bit different because our aim and objective is really to come up with a fast converging solution. And basically, what we're trying to do on the Gauss-Seidel method is to substitute the value of your solution vector based on the last or the updated value, not on the last cycle, but rather on the latest uh, updated value of the solution vector, meaning to say that if we are dealing with a cycle, as soon as the first variable is updated, we can use that most recent update to substitute it to the next equation in that cycle. So the speed of convergence will now be faster than what is being done by the Gauss-Jacobi or the Jacobi iteration. Okay, so um, this Gauss-Seidel method is actually um, anchored on the equation upon which your if we have a set of coefficient matrix A in the form of A11 x1 plus A12 x2 plus A13 x3 equals B1, we will come up with the solution for x1 in this regard. So here your A11, sorry, your B1 over A11 will be this one here, and your A12 over A11 will be this one, okay, and your A13 over A11 will be this one. So this will all be values divided by A11. That's why if we're going to take a look at the formula later, this is simply a value divided by the AIIs. Okay, and also your second row on the matrix of equation is A21 x1 plus A21 x2 plus A23 x3 equals B2, and also your A31 x1 plus A32 x2. This is A22 plus A33 x3 equals B3. Okay, such that the value for your uh, the solution vector will now be an iterate, or what you call a fixed point iterate of x1 equivalent to b1 over a11 uh, minus, okay, the summation of uh, the two, okay, expressions here, which is simply a12 over a11 uh, x2 plus a13 over a11 x3. Okay, so notice that the a11 over a11 x1 is not included here, such that the summation will actually be one less the number of expressions or the number of rows and columns, okay, in the unaugmented matrices. So if you have 3 rows and 3 columns here on the coefficient matrix, then the summation series will be 1 less than 3. And so is true with our value for x2, which is b2 over uh, a22, okay, minus the summation. Now we skip uh, a22 and start with a21 here, all over a22 x1 plus a23 all over a22 kx3. Okay, so the last row equation will therefore be equivalent to x3 is equal to b3 over a32 minus the summation of uh, a31 all over a33 x1 plus a32 all over a33 x2. Okay, so these are the fixed point iterative equation that would be the basis of the cycle uh, process, the process upon which your new solution vector is being updated. But here you will notice that the value for x1 here is actually an iterate, okay, an iterate of this the second iteration, not the first iteration. So this is actually in terms of uh, a k plus 1 iterate, if this is your k iterate, okay, and this is your k iterate here. The new value of x1 here is already on the sorry, this is a k plus 1 iterate. Okay, so this x1 that will be substituted on this x2 k plus 1 iterate is actually the updated x1 k plus 1 iterate, and not this value which is still a part of your x k iterate, okay, the previous iterate. And so is true with this one. Your x1 will be a part of the k plus 1 iterate, and your x2 here now will already be a part of your k plus 1 iterate. Unlike x3, which is not yet computed here, we don't have a choice of getting the new or the updated x3 iterate here, because there's not yet any value of x3 except for the old iterate, which is at xk del. So that is the main difference between the Gauss-Seidel approach and the Jacobi approach. Okay, so and one more thing about the term here in the parentheses is actually a summation series involving j equals 1 to n of your aij over aii, provided that j is not equal to I. Okay, So this makes your summation series actually 1 less than the number of rows and columns, or columns rather. In other books, this summation series is written in the form summation j equals 1 to I minus 1 of your aij over aii xj plus. So they skip the value of j equals I, so you will start now with j equals I plus 1 to n of aij aii xj. So this is now a form which is equivalent to this expression here on top. In my MathCAD program, I will be using this form because this is easier to handle rather than this, because if your index here is equal to 1, then I will have a 0 of value here that makes my whole expression unsteady. Okay, so you need a lot of additional conditional statement to place in your program to make it stable. So I already discussed to you how the Gauss-Seidel approach works on my last video, um, using a manual solution like this. So, and I have proven also that in my Gauss-Jacobi solution, I need 9 iteration to come up with a precise answer, while in the Gauss-Seidel equation or Gauss-Seidel formulation, I only need 6 iteration to come up with an exact answer. So to give you now a a programming solution to Gauss-Seidel iteration, taking note that the formula I derived a while ago is this one, okay, in which I only separated the summation of j. So these two terms here actually involves a summation of j equals 1 to n of my aij all over aii of xj, not including j equal to 1, or j must not be equal to I mean. Okay, so when I count here 1, 2, 3, and then I have an I minus 1 I. So if my counter starts from 1, 2, let's say 3, and then I have an I minus 1 I plus 1, that n. So I just remove this. I just let this part of the summation series non-existent. Okay, since in our analysis a while ago here, take note that the a 1 here is not included, the A22 here is not included, and the A33 here is not included. Hence, we have to exclude in our summation series the j not equal to I term, which will decompose this summation series into two summation series, starting from 1 to I minus 1 and starting from I plus 1 to n. So these are just equivalent equation, but I prefer to use this one because this is more stable in terms of my MathCAD programming platform, and I have to do additional conditional statements to make my equation, if I use this, stable. Okay, and if I now I will now show you how it is done using the MathCAD summation series. So I just copied, okay? I just copied this equation here um, in terms of the initial format, and I've just placed an if statement here. If j is equal to I, then the value is not considered, and if it is j not equal to I, it is considered. So this is just the term that the conditional statement that I place, and I end up into this tree, uh, a solution vector in my second iteration, which is exactly the same as my solution vector here in the manual computation. Okay, so 18332312338 and 1062 are simply the same as this one here. And if I am confident with my formula here, I simply copy and paste it here until at the sixth iteration I come up with exactly the same answer on my solution vector. So this is just the same as my previous iteration is. But this is directly done using my MathCAD equation. Okay, so on the next video, I will be discussing to you the SOR method, uh, which is again an enhancement or a refinement of what the Gauss Seidel is. And let's make some critical analysis on the speed and the convergence and divergence of the SOR compared to the Gauss Seidel. Thank you very much for listening, and I'll see you on the next video.